In this video, we learned the last topic of this chapter that is called Pthly increasing Pthly annuities. The section title is a little awkward, right? There are two words with the same Pthly. They have different meanings. I also put here that recall in the previous section 4.6, not 4.7. The title is Increasing Pthly Annuities. And we know in that content, what we have is 1 over P is the first payment, 1 over P is the second payment. For the first P payments, right? They are the same. In the same year, the payments are the same. So they have the same size in each year. And then in the second year, we have 2 over P, 2 over P, 2 over P. So this is P payments in year 2. They all have the same size, 2 over P. And so on. In the last year, it will be N over P for P times. So that is what we refer to as increasing Pthly annuities. So this means there are P payments. Okay, it's actually, so P equal payments each year. The meaning of increasing is from year 1 to year 2 is $1 to $2 to, and so on to N dollars, right? So the rate of payment each year increases by 1, but within each year, all the P payments are of the same size, which is the corresponding year I divided by P. So in year 1 is 1 over P, in year 2 is 2 over P, etc. That's the setup of section 4.6. Today we're going to learn a different thing. So things are still increasing, but it's not year by year. It's actually each by each, right? So here it's not each by each. That's because in the first year, all of them are the same. In the second year, all of them are the same. Now we want each one to be different. So that's why we have another word Pthly down here. The first Pthly increasing, which means among all the payments, they are increasing, okay, comparing to the previous one. So now we're going to set up things very differently. And I start up with what the textbook teaches. By the way, I should mention that is not exactly what I prefer. I believe the second method I'm about to introduce is actually easier to understand. So here the payment, the size of the payment is awkward. It's actually 1 over P squared. Here is 2 over P squared. So here you know it's going to be P over P squared. So even in the first year, all the payments are different. It's 1 over P squared, 2 over P squared. Of course, we can factor out this P squared because all of them have the same one. After we factor out this P squared, we still have 1, 2, 3, 4, all the way to P, right? And within the same year, the sequence is increasing, right, by the same amount, okay? And obviously, that's something we are going to expect. P plus 1 over P squared goes all the way to here. It will be 2P over P squared. Goes on. What would be the last one? Last one would be NP divided by P squared. Again, you know, the setup is a little awkward, but nevertheless, we can study the present value of a sequence like this. Fundamentals, right? So in order to find the present value, all you need to do is to do a proper discounting. The first payment is this. It's made at 1 over P. So it's V to the power of 1 over P. The second payment is of size 2 over P squared and is made at time 2 over P. Goes on. The last payment is MP divided by P squared and is made at time N. If you want, you can write time N as MP divided by P. Okay. So this is unusual, right? This is not something we are comfortable with, but of course, you can. What I can show you is why I can take this out, right? And what can I do? I can introduce something to replace V. Let's let what we usually don't use. Let's use U. Let U be V to the power of 1 over P. So 1 over P. For some reason, my pen is not working. You know it's 1 over P. Huh? So let me put it in slash. So U. So hold on for a second. I probably need to disconnect my pencil. Okay, let's resume. So here is what I want for V for U. U is nothing but V to the power of 1 over P. So now what I can write is 1 times U, 2 times U squared, 3 times U cubic, goes all the way to NP times UN. Okay, so this is essentially what I will be getting. Here's NP. So this looks very close to what we studied before, right? This is an increasing annuity due annuity because this is a discounted annuity immediate. This is what we studied before, but of course, if you want, you can also apply the usual trick. That means you can times by U on both sides. Then this becomes U squared, 2U cubic, 3U fourth, all the way to NP times U NP plus 1. So now you would know what I would do next, right? So it's basically minus each other. I get 1 minus U. Leave my factor out. I do the cross. Right, and then this part is it's a standard geometric sequence. You can compute and get everything. That's what we have for the present value. And now let's introduce a notation and put everything in a nice box. So we have I. Right after I, we're going to put upper P. So that denotes for this sequence, each payment is increasing after the previous one. So that is refers to the first Pthly. And then we have the second Pthly, which we write upper P down here. And then we have angle N at I. So this equals the annuity due paid Pthly for N years at interest rate I minus NVN divided by IP. Arguably, this is quite complex, right? It's a lot more complicated than what we have seen before. But nevertheless, if you recall what we derived just in the last section, this is So let me get a highlighter. So here is a standard annuity due, but the difference is here, right? This is a Pthly annuity due. The rest is the same. So that is the difference. If you have increasing sequence, you are going to change a little of the first term in your numerator. Okay. I mentioned this is not good. That's the reason why I didn't want to spend too much time on it. I'm going to use an example to demonstrate the second method is better. So at least to me, you know, I always go to the second method. What we have is we want to determine the present value of $1 at the end of first quarter. So let me draw the graph, then you will see. So it's quarterly, so it's there are 4, 1, 2, 3, 4. $1 here, $2 here, $3, $4. Okay, and you continue the same trend for the second year. So here would be 5, 6, 7, 8. For how long? For 5 years. So you would know here you would get 20 because there are 20 quarters in 5 years, and at each one corresponding to the quarter number. So this is the first quarter, second quarter, third quarter, fourth quarter, fifth, sixth, seventh, eighth, all the way to the 20th. That's why I know here is 20. What I also know is the effective interest rate per year is 4%. It's always quoted as the annual rate, and even I don't tell you it's going to be the annual rate. So this is obviously different from our standard setup, but it's very easy to convert. All you need to do is to times by p square. Right? If you times by p square, the payment becomes 1, 2, 3, 4, all the way to p, and then to np. That is pretty much what we have done here, right? And p here is 4. So that means if you want to apply the previous formula, it will be I. So here is not p, it's 4. And obviously, this is also 4 for the length of 5 years. So then formula will give you the everything, but I don't like that method. So what I like is to more or less directly analyze this. I don't want the setup. The previous setup is actually a little awkward, you know, for if you look at the size of the payment, right? So the what we handle in this question is more standard. We like this. We like to see 1, 2, 3, 4, 5, 6, all the way to whatever the number we want, right? Because it's familiar to IA, a standard increasing annuity immediate, right? But the question is, we need to make some magic for time. So this time is year. So we will need to switch from year to quarter, right? So if I switch to quarter, what I have is 0, is 1, is 2, goes all the way to 20. 20 at 20, right? So now time unit is quarter. So 20 means 20 quarters. Well, of course, it's 5 years. So this is a standard increasing annuity, right? We already know. So what I'm looking for is IA. I just need to look for how many periods. Okay, and then I need to know the effective interest per unit time, which is per quarter, which will be I4 over 4, right? And I4 over 4 is very simple to figure out. This is nothing but 1 plus I to the power of 1 over 4 minus 1. So I will get the result. This is about 0.9853%. The rest, it's a lot simpler, right? Because with this, I know the formula will be A20. Let's put something to replace. Let's call it J. So it's at J minus 20 times, okay, 1 plus J. So the discounting will be you will need to use this new effective interest rate to do the discounting instead of using I. Okay, and when you divide, you also divide by this new interest rate, because this J is the effective interest rate per quarter. And quarter is exactly the unit time we want. So that's why the second method should work a lot better, right? Because that is something we studied before. Increasing annuity is something we studied before, right? So that's why I mentioned this is the what I prefer to do is to do the time change. I change the unit of time from year to the frequency I want. If it's a quarterly problem, I convert it to quarterly. If it's a monthly problem, my unit time would be 1 month. So I will convert to the exact time period I need for the question. Okay. The accumulated value is always easy, right? So we have the same notation, I R per P. That means the payments are increasing, IS. And we have another P for n years. This will always be 1 plus I. This is the effective interest rate per year raised to the number of years. So one thing I need to mention is the payments sequence for this is 1 over P squared, 2 over P squared, 3 over P squared, goes all the way to NP over P squared. Okay, it is not 1, 2, 3, 4 goes all the way to NP. So in order to get what we usually see, this is usually what we see in the question, like in the previous one, you will need to remember to multiply by P squared. Okay, that is something you will need to remember to do, right? Otherwise, you will reduce the number by P to the square. Okay. Of course, that is for annuity immediate. The next thing is for P3 increasing, P3 annuity due, right? So I don't do the mathematical work anymore. That's because we always know IP. So here will be double dot, right? A double dot. Okay, so double P and I. So this is exactly the same as what we just had for annuity immediate. Numerator is the same. What will change is the denominator, right? Previously, we divided by I R per P. So if you recall, it's I R per P. That's for immediate. So since we are dealing with due, so it will be due R per P, right? So you should be able to figure out the same notation for the accumulated value. So it's also S double dot R per P and go N. So I believe you are able to figure this out, right? It's simply 1 plus I to the nth times the present value. So let's try example 4.21. So we want to know the present value of $1 at the start of first quarter, 2 at the second, and it goes on for 5 years. The effective interest rate is 4%. Of course, this is a lot easy because we already did. So you can just use the previous result to times by a factor to do this. But nevertheless, we can assume we don't know anything. So let's do this. I use my time unit to be quarter. Meaning I will use the second method instead of the first one. You can take a look at the textbook for the first method. 1 at time 0, 2 at 1, 3 at 2 goes on for 5 years. right? The annual effective interest rate is 4%. So this is nothing but increasing annuity due, right? For 20 periods. This 20 means the number of unit periods, right? So here we have 20 quarters, so that's why I put 20. So let J be the effective interest rate per quarter. So of course, we already did J. J is 1 plus I to 1/4 minus 1. So this is the effective interest rate per unit period, right? In this case, it's per quarter. So the quarterly interest rate. Then you already know, right? So this is the annuity due 20J minus 20 times the corresponding discounting. So this has to be discounted by the effective rate of my J. So this is 1 plus J negative 20. Because this is annuity due, so I will need to divide it by D. I can use D because we usually reserve D for the 1 year unit, right? So here is J, so it will be J divided by 1 plus J. So I don't have any notation. So this is the corresponding discount rate per quarter. It's the corresponding interest rate divided by 1 plus the interest rate. But I don't want to use D because usually we reserve D as I divided by 1 plus I. But nevertheless, textbook use the D anyway. But I don't want to do that. I just want to keep as J divided by 1 plus J. Everything then can be calculated relatively easily. That is because your calculator has a built-in function to compute the present value of annuity due. Once you know this, the rest should be straightforward, right? Once you know present value, future value is rather obvious. So I guess that is the end of chapter 4. So in general, chapter 4 continues what we started before. We are interested in annuities, right? So in fact, in chapter 4, we mostly focus on annuity immediate and annuity due. But there is a possibility that I include the concept of perpetuity or continuously payable annuities. For some reason, our textbook doesn't mention, but that does not mean it's not important. Okay, let's conclude this chapter